Okay, so last talk of this morning session from Antti Kupiainen. We'll talk about quantum Liouville theory.
Okay, I want to thank the organizers for the invitation to here. I actually missed I wasn't able to be in the original program, so I'm very happy to be in this program now. So what I want to talk about is some attempts to understand the Liouville theory and what I call quantum. So let's see what that means. So this is joint work with Vincent and Remy. So the background here is conformal field theory, which is probably familiar to some of you. So conformal field theories are sort of scaling limits of statistical mechanics models at critical points. Two-dimensional conformal field theories also were very prominent in the development of string theory, and four-dimensional ones are currently very prominent in physics of physics beyond the standard model, let's put it like that. And they have really a lot of structure in every dimension, and they are supposed to be strongly constrained by something which is called conformal bootstrap. So I will come back to that. So what I want to describe is somehow how to approach the problem of conformal bootstrap in the Liouville theory, which is an interesting conformal field theory itself. I'm not going to review you at all why it's interesting. I think most of you have heard talks about that. But it's certainly supposed to be a building block of two-dimensional gravity, and in some sense it's a very universal conformal field theory in the sense that many others are sort of encoded into it in one way or the other. So before that, let's put some impressionistic background of conformal field theory first. So you can formulate all kinds of axioms for it, and there has been a lot of this stuff for a long time. Let me just give you sort of impressionistic physicist axioms for it first. Some things which, and this is from the probabilistic point of view. There are algebraic formulations which are quite different. So there is something which, let's call it expectation. So you should really think about it as expectation, but sometimes it's not normalizable. So I denote it by brackets. Yes, here. Then there is something which is called spectrum. It's a certain set of random fields, which are called primary fields. And then you are interested in computing correlation functions of these random fields, averages in that expectation. These primary fields, the name primary comes from the fact that they have simple transformation laws under conformal transformations. For instance, in 2 dimension, if the field is a scalar field, it just has this very, transforms like with the power of the Jacobian of the map. And that power is modulo 2 is called conformal weight. Now, another very important aspect here is something which also has a strong physics background. So it's usually called the operator product expansion, although here we don't have any operators at the moment, as we will have later. But in practice, it means that if you have two such primary fields within a correlation function, and you look at these primary field correlation functions and take the 2 points which are closest to each other, then you have actually an expansion in terms of reducing the number of fields. So the two I and j disappear, and there is a k there, and some universal coefficients here. They are completely determined by three-point functions on the sphere. Okay, so here we are thinking about formulating the theory on an arbitrary manifold. But once we take the points together, they are completely determined by three-point functions on the sphere. And these indeed, because of conformal invariance, are completely just numbers. They don't depend on the points. and those numbers are usually called the structure constants of the theory. So this is one of the basic data of conformal field theory, are these structure constants. So if you have such a formula, then iterating this formula, you can just strip off all the fields here, one after the other, and reduce them to just these structure constants. So all the correlation functions will be completely fixed by the structure constants and one-point functions on the surface. So the upshot is that if you succeed doing like, in order to now, if this is true, then you should just to solve the conformal field theory, you should try to find the spectrum and the structure constant. Okay. Now, bootstrap usually refers to just this procedure of operator product expansion where you can reduce the number of points. But in particular, if you say take a 4-point function and do this reduction by say combining first the I and j to m, or you could also rather combine the I and k, I suppose, yeah, and get a different decomposition. So you get two different decompositions. These were depending on the structure constants. These depend on the structure constants. You get a quadratic equation for the structure constants. And indeed, that's a complicated equation, but that actually can, in many instances, one has found solutions for these equations. The famous one goes back to Liouville, Bolikov, and Samolochikov, who solved it for the so-called minimal models, this equation. So in particular, the Ising model in 2 dimensions. And then about 10 years later, Zorn and Otto and Samolochikov found the solution for the Liouville model, the so-called DOZZ formula. And then much later, quite recently, this same idea of bootstrap has been very successfully carried out in 3- and 4-dimensional conformal field theories, starting with the work of Rychkov and others. So the question is, can one derive these operator product expansions and this idea of bootstrapping in a non-trivial conformal field theory, derived from basic principles, some starting point? So the setup, we are going to work with this conformal field theory, which is given by functional integrals. So the functional integrals, so that's a explicitly probabilistic formulation. So what in Surav's talks where he was starting with a Euclidean framework for Young-Mills. So here, this is the Euclidean functional integral. You have an action function, you integrate over some fields, and this expectation is just defined. You try to define it through such an integral, making sense out of such an integral. And the action function for the conformal field theory should be a conformally invariant functional, and it should be sort of local, depending on only on the fields or their derivatives at the point, and sort of integrated over the surface. And the primary fields are also then some functions, local functions of the field. Now, as was already pointed out by Surav, the reflection positivity is a very important concept here. So that connects this probabilistic language to what I called quantum. Namely, these are supposed to be quantum field theories and not just probabilistic things. And to have a quantum field theory, you need to have a Hilbert space, operators acting there. In conformal field theory, that's especially interesting because you have a rich algebraic structure which takes place in this Hilbert space. And there is nothing of that at the moment once we have the expectation. So we have to build this sort of bridge there. So that goes via this construction of reflection positivity. So let's take the manifold of cylinder. So the first, so there's an R which I call time, and then the rest I call theta. Then you can define a reflection in time in the cylinder around time equals 0. And let's look at a particular set of observables which depend only on the fields on positive times. Okay. Then the conformal field theory, the definition, it's reflection positive if the following expectation is positive, non-negative, namely you take this f and you reflect it. Okay, so this guy lives on positive times and this on negative times, and once the reflected thing is, if this expectation is positive for all such observables. If that's the case, then we can, this gives us a sesquilinear form, right? I mean, you can define a scalar product, and then, so let me denote the scalar product with the usual, not with the brackets, but with the parentheses. And then the physical Hilbert space you get just by completing this set of functionals in this, modding out zero norm states and completing in this scalar product. Yeah. So that's the physical.
What is this notation, f tau of f? I don't understand.
Okay, tau is the reflection in time.
F tau.
Tau, obviously, if I tell this extends to the fields, right? So tau of phi is phi at minus t, and then it extends to the functionals of the fields in an obvious way. Okay, so if I have a functional of the fields which depends on the fields on positive times, then tau of the functional depends on the field on negative times. All right? Nothing. Maybe it's a bit too shorthand notation, but yes.
Is there a global dynamics going on? Because you're
There's no dynamic at the moment. There's no dynamics. It will become next slide. Okay. Okay. Wait for a second.
what is time here? I mean,
Oh, I took. No, it's just a parameter. I took the manifold to be a cylinder. Okay.
okay.
Okay. Is this clear now? This definition. Okay. Once you have that, it's obvious here that this should really depend only on the scalar product should be written in terms of only the fields at time zero, because this guy sort of, there are the guys on the positive and on the negative, and they meet only at origin, and indeed that you can do. And let me explain that in the simplest possible case, the two-dimensional free field, which everybody is familiar with. So the simplest conformal field theory is the two-dimensional free field. Here is the action. The action is supposed to be quadratic for the free field. And so there is the gradient phi squared. If you are in a general setup, then there will be a covariant derivative, etc. And then there can be a linear term also. And the linear term, again, to be invariant, you put here is the curvature, Ricci curvature of the manifold. So you could take such an action functional. And let's just do what the free field looks like. This free field looks like in the two-dimensional situation. So we are going to construct the functional integral on the cylinder, which is the time times an angle. Okay. So this is done in terms of Gaussian free field. The free field is slightly different from Gaussian free field. Gaussian free field is one aspect of it, but there is another aspect which is the constant here. So the free field is defined as follows. So you take the Gaussian free field on the cylinder. Gaussian free field on the cylinder, of course, not it's defined only up to a constant. So we take a particular realization by normalizing it so that at origin, at zero time, is integral around the cylinder is zero. Okay, so this is a well-defined distribution, Gaussian free field on the cylinder normalized this way. And then it's important not to forget the constant, which is absent in the Gaussian free field. So we put that in here. And then due to conformal invariance, there is also something which turns out to be a drift term coming from this Q factor here. Okay, so that's the definition of the free field on the cylinder. Okay, and then what is the bracket? The expectation. It will be just the ordinary expectation of the over the Gaussian free field, and then integration over the constant. And there is a weight which comes from this Q factor here. I'm not going to do you the reduction from here to here. That's easy to do. let's just take axiomatically that's what the two-dimensional free field on the cylinder is. So it's Gaussian field, free field, and the constant mode added onto it. So what does the Hilbert space look like? Well, I told you that you want to reduce it to the time zero degrees of freedom. So let's decompose the Gaussian free field to three independent things. So I take a Dirichlet field on positive times, a independent Dirichlet field on negative times, and then take the rest, which is constructed out of the field at time zero. So take the var phi to be the field at time zero, the free field at time zero. I will call p phi its harmonic extension to the whole cylinder, and it's well known that you have a decomposition into three independent pieces of the Gaussian free field, like here. So if we have that decomposition, we can write our inner product. So if I take this, what was the inner product? I took the functional of the field and the reflected of the other one, and expected value on the cylinder, which by definition is given by this integral here. And f depends only on x plus, right? Because it depends on the positive times. Tau g depends only on x minus because it depends on the negative times. So I can split this expectation into expected value over phi, x plus and x minus, and those two are independent, so they factorize. Okay?
Yeah, absolute value on C, right, in the integral? Or
Absolute value where?
in C, no.
No. It's essential that there is no absolute value in C. No. Okay? C runs from minus infinity to plus infinity. Okay? You look puzzled.
That was the previous slide, so I think.
Let's go back. So phi and the zero mode.
Yeah.
The zero mode is here, minus 2qc. The 2q comes from the Euler characteristic of the manifold. Okay. This is a conformal cylinder. It's not a flat cylinder. It's a conformal cylinder. Conformal image of the sphere. Okay, so where am I? Okay, so that's what it is. But these are actually the same thing, because the Dirichlet field has the same law as the reflected Dirichlet field. Okay, and the harmonic extension is symmetric in time. So we end up with the following formula. The inner product defined by the Osterwalder-Schrader, the reflection positivity formula, is given by an inner product in the space, L2 space of the constant mode C and the free field on the circle. Namely, if you take F, you integrate out the everything else except the thing coming from the zero, the time zero field. So you take expected value over the x plus. So you get the functional of the field at time zero. And then the inner product is just, after that such an operator, the usual L2 inner product here. Okay? So the Hilbert space, which I described to you abstractly, is concretely just the L2 space of the zero mode and the free field on the circle. And this is a unitary map mapping the two pictures to each other. Okay, P here is the law of the field at the circle. That's the 1 over F noise field, just given in terms of the random Fourier series. So that's what this object is here. Okay, so that's the description of of the quantum free field. Not a very deep object, but but what do you have there? Well, how does the quantum mechanics arise here? Well, time translation acts on the functions of positive times. If I move them in time, they are still functions supported on positive times. So there's actually that if I call the time translation T of S, then it maps this space of observables living on positive times to itself, and that's obviously T of S is actually a group, or semi-group, because you have positive times. Then obviously once I map it to this space here, I get a semi-group acting there, and the generator of that semi-group is called the Hamiltonian operator of the conformal field theory. This is a completely general construction of quantum field theory, nothing to do with even conformal field theory, but but here it's very explicit. Of course, in the free field case, you can explicitly compute it, and the result is the following. So there are two pieces in the Hamiltonian. There is just free motion of the constant mode. That's a Schrödinger operator of a free particle. And then there is a sort of Laplacian in the free field on the circle, which can be described explicitly in terms of these creation and annihilation operators, which are just differential operators in the modes of the 1 over F noise. Okay, so that's the Hamiltonian of the Gaussian free field. What is the spectrum of the Gaussian free field? The primary fields are something which are called vertex operators, so the exponentials of the free field, defined by the Wick ordered, normal ordered, which means just that you renormalize them by their expected value. And these guys you can compute their conformal weights easily, and they are given by such numbers here. Then you can compute the corresponding states in the Hilbert space. How would you do it? Well, you just do the following. You put one of these guys at time t, take the t to infinity, and let it evolve. And the result is very simple, of course, in the free field. The corresponding states are just these functions of C here. So the eigenfunctions of the Hamiltonian, which I just wrote here, second derivative has an eigenfunction, exponentials are eigenfunctions with these eigenvalues. You see, these are not normalizable at all. This increase or decrease at plus or minus infinity depending on the sign here. Only if this number here is purely imaginary, these are actually in the spectrum of the Hamiltonian. Hamiltonian is a self-adjoint operator. It has a spectrum. It's a positive self-adjoint operator. It has a spectrum, and the eigenfunctions or generalized eigenfunctions are the ones where alpha is q plus ip. So q cancelling the q here, and p being real and ip. Okay, so that's the spectrum of the free field theory. You can go on in the free field now. You can actually then realize the conformal symmetry. These psi's are actually highest vectors of two Virasoro algebras. Namely, there is an algebra of operators defined with very similar formula as the Hamiltonian I wrote here. I'm not going to write it to you. So there is similar sum here to here, so they're concrete operators. You can check them, and they define you. They define you. The eigenfunctions of the Hamiltonian are highest weight vectors, which are annihilated by some positive index operators, and then the operators satisfy this algebra where the central charge is given by this number 1 plus 6q squared. Okay, and finally in the free field, the operator product expansion is also very simple, because every correlation can be computed in the Gaussian free field. They are exponentials of the field, so if you do then the Gaussian integral, you get such a product because the green function is logarithmic, so you get the product like this. And then there is an overall delta coming from the fact that the Gaussian from the integral over the zero mode. So the Gaussian free field has a very simple operator product expansion. Once you multiply two of these exponentials together, they just add up the values, and everything is completely explicit, of course. Now the problem here is that the spectrum is not closed under the operator product expansion unless q equals 0. So actually, to get the non-trivial conformal field theory here, the only choice to you here is to take the q factor to 0, and you get the c equal 1 theory. Okay, that was the exercise of what is the connection between probabilistic free field and the picture of quantum conformal field theory. So let's make things less trivial and consider the Liouville theory. So Liouville theory is a deformation of this free field theory. The following deformation, I write it in general manifold first and then we specialize. So you just add another conformally invariant term. This is the free field action, and you can add a term like following. You take exponential of the free field and integrate it over the volume on the surface, and put a constant mu here, which is called the cosmological constant. And to have conformal invariance, then the number q, which occurred here, is tied to the gamma, which occurs here, by the following formula. Okay. Now this is the heuristic definition, and once you do it precisely, you end up with the following expectation. It's exactly like in the Gaussian free field. So you integrate over the constant mode, e to the minus 2qc, expected value of the Gaussian free field, except that you have the Liouville term here. Okay, so we measure the there's a Radon-Nikodym derivative added, which is here, and I'm using the normal ordering here. So explicitly, again, what this really explicitly is the Gaussian free field. There's the zero mode, and then there's normalization, and this object here means the multiplicative chaos measure, which was discussed by Jason just a moment ago. Okay, so that's the definition of the expectation of Liouville theory. Okay, so what can we do with this? Well, the first question is what are the correlation functions? What are the primary fields and what are the correlation functions? We have an expectation, so what are the which correlation functions make sense? This is the result. If we take the alpha i's real, so I'm considering the vertex operators just like before, the e to the like in the Gaussian free field, it's exactly the same operators. I'm sorry, the fields, not operators. Then this correlation functions exists if the alphas satisfy these conditions. So their sum has to be big enough, and they are not supposed to be too big themselves. Okay, this condition is not so difficult to understand. You see, if you look at this expectation here, the c integral clearly has no problem of convergence when c goes to plus infinity, because the phi here is proportional to c, right? So this damps everything at plus infinity. So unlike in Gaussian free field, where there is not this term, here this term kills the c going to plus infinity, and only minus infinity is an issue. This guy increases at minus infinity, so this is bad. Okay, so if I expected value of 1 is not there, so this is not normalizable measure at all. But if I have the vertex operators which all carry exponential of alpha times c, then they can help and make this convergence, and that's this condition here. This is a multiplicative chaos result, which is deeper, and let's not go to that here. Then, okay, so that's the correlation functions. Then what about the structure constants? Well, the 3-point functions actually are given by an explicit expression. I told you that the DOZZ found a formula for them, and we were able to prove that formula quite recently, and I'm not going to say anything about this because I think Guillaume Remy will talk about a little bit about this and its generalizations to other situations. So let's just keep it like that. So anyway, the Fij case, the structure constants, we know in this theory. So what's remaining is the bootstrap. Okay. Oh, well, that was the proof of those, but let's skip it. So what is the Hilbert space for the Liouville? Okay. Well, the Liouville is also reflection positive because, you are just dressing every correlation function by these guys, and this is an integral over the cylinder, minus infinity to plus infinity. You can just divide it into two pieces which are reflections of each other. So the inner product is just like, that's the definition. And it's like in Gaussian free field, except that there is this dressing by this exponential of the Liouville term from 0 to infinity. Okay? So again, we can realize the Hilbert space of Liouville just in the same as Gaussian free field in L2 of the constant mode and L2 of the free field on the circle. Only the map is very different. It has this very complicated dressing transformation. Okay, so it's the same Hilbert space. Well, the abstract story goes like before. The generator of time translations is a contraction. It's easy to see. It's a contraction, and its generator will be a positive operator on the Hilbert space. And the Virasoro algebra goes also through here. That goes through by the so-called stress energy or energy momentum tensor. There's a story why all of this goes through. I'm not going to tell you about that because that's again a slightly longer story. But there's a concrete field which is given in terms of quadratic in our basic field phi, quadratic and some derivatives involved there. And once you take that and consider correlations of the vertex operators and these products of this T, then these are actually defined and actually completely explicit. They're defined as long as these points are non-coinciding. The reason for that is something, are certain operator product expansions which you can actually prove here. These are called the conformal word identities. So within the language which I introduced in the beginning, in correlation functions, these two fields actually can be, their product can be replaced identically by this combination here. And these two fields can be replaced identically by this combination here. So actually what happens is that all these insertions here just produce explicit factors times derivatives of the original correlation functions. And if you know that the original correlation functions are smooth, then you're done. And this was recently proved by Oikarinen. Okay, so once you have that, then you get Virasoro algebra in the following way. Take a functional supported on positive times. So I apply the map which maps that to the Hilbert space, and then define the Virasoro generator as the Fourier coefficient of taking the energy momentum tensor at times 0, integrating it over the circle, and mapping it to the Hilbert space by U. Okay, that's a concrete formula. And, and that way defined, these guys extend to densely defined operators in the Hilbert space which satisfy this algebra. So conformal algebra with central charge 1 plus q squared. Okay, so those are the sort of things we know about Liouville theorem. Now, the remaining question is, how does this representation here? So there's a representation of this infinite dimensional algebra. How does it reduce? So what is the spectrum of the theory? Can we use this algebra to actually solve the theory? And let me explain this to you, something which in physics has a very fancy name, but you will see that this will be very simple. It's called the mini superspace model. and it's the following. So remember, everything was given in terms of Gaussian free field on the, I have the Gaussian free field on the cylinder, which was normalized so that its integral at time 0 around the cylinder is 0. Okay, so I can decompose that now into two pieces, namely sort of its integral around the cylinder, and that's just the Brownian motion in time t, and then the rest, which is something which has now 0 integral around the cylinder everywhere. Okay, so that's a simple decomposition of the free field, probably familiar to most of you. So then the Liouville field then has this, becomes the following. There is the constant mode, there's a Brownian motion, a drift, so there's a two-sided Brownian motion on the cylinder, there's a drift for the Brownian motion, both sides, and then there's this rest free field path. And let's not now just make the brutal approximation where we just forget about the rest altogether. This is called the mini superspace model. So we only have the constant mode, okay? So we are sort of forgetting about the Gaussian free field, except the Brownian motion, which is generated by the motion of the constant mode. Okay? Then we have an expression which every probabilist probably recognizes. So the expected value is this integral over c, and the Liouville term like before, except that now it's just a Brownian motion with a drift here. Well, you can probably recognize this as a Feynman-Katz formula, and you can if I now do my Osterwalder-Schrader, my reflection positivity construction, then the U map is just given by the following formula. I integrate out just the Brownian motion. There's nothing else in my randomness, and then it's a simple exercise to see that what you are really doing here, the generator of now the time translations, is just by a Feynman-Katz formula given by just the following operators. There's a Laplacian in the C, second derivative, and then from the Liouville term you get the exponential interaction. So that's the Hamiltonian is a Schrödinger operator describing scattering from a wall potential. This goes to infinity, this potential at plus infinity, and goes to 0 at minus infinity. So you feel no potential at minus infinity in C, and you are completely dead at plus infinity. Okay. What is the spectrum? Well, in such a case, the spectrum is determined by what the operator looks like at infinity. So the spectrum is just what is the spectrum of the Laplacian? That's of course p squared. The eigenfunctions go like e to the IP pc. So there's a half p squared plus q squared. So that's what the spectrum is. And you have generalized eigenfunctions, which are sort of like if you have studied scattering theory ever, then this is a simple exercise in scattering theory to find them, they look like plane waves e to the IPC at infinity, and plus infinity they go to 0. And since they have this condition that they go to 0 at plus infinity, that they have sort of a fixed. You don't have for e to the IPC and e to the minus IPC as your eigenfunctions, but you have just one combination. And the combination is a linear combination of waves which go one way or the other, and the coefficient here is a reflection coefficient, which actually has something to do with the reflection in Liouville theory, which some of you might know about. Okay, so that's a very simple model. Of course, we can understand everything here, but let's try to do this bootstrap in this super simple case. So how would it go? Okay. So we have just this Brownian motion model, so we can calculate everything quite explicitly. Feynman-Katz formula. What does it say? I take a guy at minus t, guy at origin, and guy at t positive time. How do I write this in terms of an inner product? Well, you can view it as an inner product of two states. One on the negative, reflected to the negative times, and one at the positive times. So with the formula, it comes as follows. I have the semigroup generated by the Hamiltonian acting on this state, and there is this Q factor, which is always, remember, here. The Q factor enters here, so that's slightly annoying, but that's how it comes. And there is a similar thing on the left-hand side, and then at time 0 there is just this function here. So the three-point function at general times looks like this, and the structure constants, remember, where you chose them by taking specific times. So I will take the times to infinity, and to have a limit I have to multiply by a factor. And once the dust settles, you end up with the following formula. So the factors are just the eigenvalues of the Hamiltonian at these functions here, and you get a limit. You get the three-point function expressed in terms of an inner product of a state, another state, and this function at time 0. Actually, you can carry out exactly the same calculation in Liouville theory. You can write the Liouville structure constant in terms of inner products of states, exactly in the same way. Okay, so what is the bootstrap? Well, let's look at the 4-point function. So what is the 4-point function? I put something at time 0, something at time t prime, something at minus t, and some capital T, and something at minus little t. Okay. Remember, the bootstrap was that I took 2 points together. So let me first take these guys to, as before, to 0 and infinity, to minus infinity and plus infinity, and then I end up having now the Hamiltonian acting, the Hamiltonian semigroup acting on the state created by this. There is this guy. If you go from here to here, you get e to the minus t Hamiltonian, and here you get the state from here. So the 4-point function is such an inner product, where the fusion is now taking little t to also infinity. So the point of 2 is moving towards the point alpha 1. The bootstrap is nothing but spectral theorem, because this is an inner product where the Hamiltonian acting on this and that. So let's use the spectral theorem, where I can write the semigroup as an integral over the spectrum of the exponential of the eigenvalue times projection to the eigenstates. I write it in the physicist notation here. So once you plug that into here, the 4-point factorizes as product of two 3-point functions, and you end up with a formula like that. So in the mini superspace model, the bootstrap is just very simple calculation like this. The 4-point function can be factorized as a product of 2-point functions and summed over the spectrum, which here is continuous, so there's an integral over the spectrum. Okay. What would it be in Liouville? So this was completely trivial exercise to do the thing when I take away the Gaussian free from the Liouville. But I think from here we learn what the result should be in Liouville. So in Liouville, the Liouville Hamiltonian is related to this Virasoro algebra. The Hamiltonian is just actually just L0 plus L0 bar. There are these two Virasoro algebras, and all the states you should have something like the following. You should have states and their descendants where you act with these Virasoro generators, like I was explaining in the free field case. And you should have highest weight vectors, just like in the free field case. The Hamiltonian acting on any such state will be given by whatever comes at the state P, and then something from the descendants. So in particular, the Liouville spectrum should look like something starting from Q over 2 and going to infinity, the spectrum of the Hamiltonian. And if this picture is correct, then this conjecture, if this is the Liouville spectrum, if the whole spectral decomposition is gotten from these states, then this leads to the bootstrap relation exactly in the same way as I did it for the mini superspace. You get an integral over the spectrum of some factors which depend on the descendants, and then the structure functions, just like there. And the only difference is that this factor is slightly more complicated than it was here. Here it was just this factor exponential of that. Here it's something which is called, which is completely explicit. It's a so-called universal conformal block. It's a completely explicit function. So that's the that's what the Liouville bootstrap should look like if the picture is correct. Numerically, this has been checked a long time ago that it certainly is correct. And if you take now the limit of this as t goes to infinity, then what happens is that and normalize it so that it either goes to 0 or blows up exponentially, so you normalize it so that you get something finite, then that limit actually becomes rather simple. It just becomes this formula here. So derivatives of the structure constants and some explicit factor. And this was actually proven recently by Bavares and Wang. So we have lots of confidence in this formula. It would be nice to be able to prove it. What we can do at the moment is the following. So the question is this business, if you want to think about it from this point of view, is how would you construct these highest weight vectors? Okay, I told you that we can we have a very good understanding of a probabilistic understanding of these vertex operators with real alphas. Okay, this is what the theorem of David, Vincent, Remy, and me dealt with. But these states here, the vertex operators should be actually complex and not real. And that's a tough issue, whether there is a probabilistic construction for that or not. Okay, so the thing we can at the moment prove is still that the spectrum starts from half Q squared. That's actually not very difficult. That the infimum of the spectrum is bigger than that follows from the fact that the Liouville Hamiltonian, in a certain sense, is bigger than the free field Hamiltonian, and the free field spectrum starts from here. And then that the infimum of the spectrum is I'm sorry, that yeah, and then that you actually get to the half q squared. You can for that you just need to find trial wave functions which get you arbitrarily close to it, and so just do a variational answer. So this is not so difficult to do. To get these guys, you need to do scattering theory in the Liouville for the Liouville Hamiltonian operator, and we have some hopes for doing that. At the moment, it's work in progress. So I think a simple thing is that the spectrum really is the complete interval from half q squared to infinity, but that what the actual eigenfunctions are, it's more tricky. Okay, so there's plenty of evidence that Liouville theory is integrable. So we have the DOS formula for the 3-point function, and we have some sort of hope to be able to do the bootstrap, and doing all this with the probabilistic means. Of course, you can sort of take the Liouville theory axiomatically and just say that it has to have this structure. Then you need to, of course, check that the structure is consistent, which is non-trivial. On the probabilistic, once we have a probabilistic starting point, which is a functional integral, then of course we can then try to answer these questions starting from that starting point, and that we think we are pretty near finishing. Okay, I think that's all. So let me just end with an advertisement of the next program here in the Newton Institute, not very far in the future, 2 months. So if anybody is interested, some of these things are going to be discussed there too. Okay, thank you.
I have a general question. I mean, if one tries to I sort of see, I mean, sort of fairly clear, probably not, it's not sort of that there is a way to make sense of the things where you take the real things in terms of some sort of condition version, I mean, versions related to the cones, and so, I mean, putting singularities at various points.
Right.
In the Jason and Scott version. But when you put the complex things there, I mean, when you start putting
well, maybe Jason or Scott should answer the question what the complex things there are. I mean, for us, the problem at the moment is that the 3-point function. Of course, we prove actually that it extends to the whole complex plane. But of course, it's not a probabilistic definition. For instance, when you even when you take these alphas, I told you the alphas have to be less than q. In that formula, I can take alpha bigger than q, but real. Then the expected value actually can take negative value. So it's clearly not a probabilistic object anymore there directly. But that doesn't exclude that there is some sort of probabilistic construction anyway. Okay, and around the spectrum, I think it's still undecided whether there is a probabilistic construction or whether in the end we have to do it by some analytic continuation trick like which worked in the 3-point function. So I don't know in the Scott and Jason and Bertrand approach whether there is a understanding. You know it better, of course, of complex alpha.
Other questions?
How do you prove the smoothness of the correlation functions?
Oh, that's usually in quantum field theory. This is not a difficult issue, but here it's super subtle. Okay, so what we did with Vincent, Remy, we proved the word identities, and we needed C2, and that was quite a job. But we succeeded doing that, but we got sort of stuck there. But now, in the end. You can do it. It was done by PhD student. beyond algorithm. Yeah. But how do you do it? Okay, that's a long story. Okay. How do you do it is sort of lots of complex analysis. You have to go through these Beltrami transforms and identities coupled with identities. So it's not only analysis. You have to use identities peculiar to Liouville theory. There are these KPZ identities which are very crucial to that. So it's a bit subtle issue. Somehow the ultraviolet and the infrared are mixed together in the Liouville model.
No more questions? Then let's thank Antti again.